Hi everyone, welcome to Module Tree of CS2024. I'd like to sincerely apologize this came a bit later. I've been in a few meetings that talked about how to rework this course as they're going about it. So I've shifted a few of the bits of content around. As we know, this course is a work in progress. But for this module, we're just going to be looking at some algorithm analysis, some details, and there'll just be a brief quiz but no specific assignment about the information on this, okay? So I'm going to go through the slides. If you feel like you've read chapter 2 yourself and you're comfortable with it, that's fine. I kind of picked out the key points and just wanted to reiterate on what I want you guys to kind of take away from this without getting too crazy with the mathematical details. Sorry, I lost my mouse. There we go. Cool. So again, this covers chapters 3 of the course or of the course textbook, and it covers these concepts of timings that we'll see inside of Python. And for most of this presentation is going to be mainly me kind of reading off some of these slides and just talk about more information of it. But I'll do a small bit of code that I'll also put into the information at the end here. Okay. So again, when we look at what this course is about, we have data structures, which is a systematic way of organizing and accessing data. And then we have algorithms. So it's essentially step-by-step procedures for performing a task. Now, you can think of this in a very realistic way. Like, let's just say that you have a cabinet, there's stuff inside of the cabinet, and you have a procedure to go through the stuff in the cabinet. So essentially, algorithms and data structures are combined in the sense that data structures are worked on by algorithms. Now, in terms of actual programming, and one important thing of this course is how do we measure if an algorithm is effective? And we do this using running time. So running time is this overall measure of how good an algorithm is. And the reason we do this is because time is precious, resources are always limited, and the hardware software that we have impacts speeds. So you might hear stories like back in the day, we only had a few megabytes inside of, before even I was around, before like we had big computers with gigabytes of data, we only had so many resources. So we needed to utilize the resources properly. Now, just because we have more space now doesn't mean that we need to stop this practice. It's still efficient to go through pieces of data, essentially in the global period where we have data on everything, and we need ways to organize it properly. Cool. So essentially, at what we're going to be looking at with running time is that while we go ahead and go through our algorithms, time will become increasingly more complicated with more advanced data structures and algorithms. But in general, you could see here that if we have a running time of an algorithm that's doing something, let's just say that it's reading out a list of people enrolled in a course, the more people in the course that you have, the longer it's going to read through it. Okay. Now, this just makes sense in any aspect. If you have pieces of paper and you have more pieces of paper, it's going to take you longer to go through them. Now, one thing I want to go back is some of the challenges we'll interfere with inside of here. So the CPU is going to share many features with your computers. And why this comes up is, let's say that you're using like a supercomputer. It's going to be able to process information at a much faster rate than other computers would. So essentially, a fully implemented algorithm must be created to execute running time experiments properly. And we might use primitive algorithm data structures when better ones exist later, but essentially to get a piece of data down to figure out where to go from there. Now, what I wanted this slide to tell us is essentially we only can do so much with our algorithms to experiment on, and we want to make sure that we do whatever experiments we do create are effective. Cool. So when we talk about running time and how long it will take to do something, we talk a lot about operations that occur inside of an algorithm. So an algorithm's operations can be condensed into primitive and non-primitive types. Some primitive operations are such as an assignment of an identifier, so x is equal to 5, type checking, so remember we have the type keyword and we put it around a variable, adding or subtraction comparisons, so is x less than y, accessing an element of a list, so essentially if we're going through list of I using our for loop or the for loop by index information, calling a function, and returning from a function, so the return keyword itself is an operation. Now, why do we call these primitive is because in Python, these are low-level instructions, and the execution that occurs is constant. So it happens immediately, right? So usually the hardware at a low level does this, so we count how many primitive operations are executed and identify this number as t. So if you go through a function, you check number once, and then you return from it, that's going to be 2 operations, and if you call that function, that's a 3rd operation. Okay, so again, why I'm talking about primitive is that whenever we're saying how many operations occurred in this function, that's what we're going to want to look at. So there's a bit of information in this slide, but what I want you to understand from here is the logic that we're going to use to analyze our running times, because based on this course and other things you might see out there, you might hear keywords such as worst case, average case, or best case, especially if you go to like other platforms, LeetCode or anything to see stuff going on. So essentially what happens with these algorithms is that they're going to change as a function of the inputs onto that algorithm, right? And we remember this earlier that if we look at our linear runtime, if we have more inputs in our algorithm, it's going to increase how much it goes by. Now, this chart is very useful because usually when we want to design an algorithm, we want the most effective best case scenario. So something like E input size would be good. And then we also have the possibility of the average case time. But if we try to calculate an input that's for the average case here, so let's say, okay, how many A's, B's, C's, and D's do I need? We will need to look at the probability of these occurring. And when you're looking at probabilities of user inputs or what a person will do with your program, it's kind of impossible, and you shouldn't assume that they know what they're doing or that they're going to do something that's kind of normal to what you would do. So what we want to do is to always look at the worst case scenario for our algorithm. So essentially, if your algorithm is linear, what happens when I put a million items in there? And then what can I do to my algorithm to make it more effective when I have a million items? Now, why do we always go for the worst case? It's not really because we're pessimistic about people, but it's more so that if we plan for the worst case, every other case will have to do better, logically, right? So if we always plan for A and D to have 5 MS, excuse me, to have an input of A and D only at the max, and we make our algorithm very effective for those two inputs, then whatever happens between the average and the best case is not necessarily of our concern because we already know the worst case is good. Okay. Cool. So a lot of this is going to be kind of mathematical, but I don't want us to go too crazy or be too intimidated by the math in here. I just kind of want to give us the functions that we're going to use in this course and some of the keywords. So there's going to be 7 running times that we're going to look at. There's a constant, which we already saw was the primitive operations. So again, for any argument n, the constant function n assigns the value c. So this is instantaneous, right? So if you do fn is equal to c, x is equal to 5, that's your constant. The next one we have is this logarithm. So what we say here is for f of n is equal to log base of n. So for whatever function that we put the value of n into, we're going to get out the log base of n. And this is for any constant b of 1. Now, one thing to note, if in your other math courses you did logarithms, the base is usually considered 10 in most cases, but here we're always going to assume that it's going to be 2, okay? So if on any of the assignments or questions out there, I'll put the 2 for most of the time, but if I forget, just assume that log base of n is log 2 of n. Okay, so what we see here now is also the conversion between these two formulas, right? Log x is equal to log b of n if b of raised to the power of x is equal to n. This is stuff we might have seen before. The main thing I want you to know is that the logarithm has a base of 2, okay? One more thing is that the running times that we're looking at here are getting longer as we're going through these functions. Cool. A linear function is what we saw earlier. X to y right here. This is a linear function. So linear is pretty common. It's whenever we have an amount of n elements, we run through each of them. So comparing a number x to each element of a sequence of size n requires n comparisons, right? So let's just say that we have a list of items that are odd and even, and we want to check if there's any value of 2 inside of our list. We will go through each of the items in the list until we find a 2, okay? So linear is what we usually see. Now we get into a bit more complicated one here. We have the n log n function, or linear arithmetic function. That's the other way that you could pronounce it. We'll call it n log n for this class. This grows a bit more rapidly than a linear function, but a lot less than a quadratic, which is squared. So in most cases in real life, n log n is what we get when we're dealing with like Chase Bank or these what are local banks in Ohio. If you're dealing with that much data, that's how much runtime you're going to see. Okay, and this assigns to an input n the value of n times the logarithm base 2 of n, which is what we saw over here. And then this is the fastest growing algorithm is n log n. So these are usually what we're going to get. In real life, linear functions are good for like basic things we do, but not for the more complex data structures. Okay. Some more functions we see in this book are quadratic functions. So f of n is equal to n squared. This essentially means that whatever value we put in for n is going to be raised to the power of 2. And this happens when we have nested loops. Let me go ahead and actually pull up our code here really quick. Hi, everyone. Sorry about the small cutoff. I just wanted to put together some code to actually visualize these functions. This will be saved for you later as well. You can see here I create different sizes of lists from 0 up to 100 and then 10,000 to 100,000 just to kind of illustrate the different sizes of data structures we'll have. So for linear functions here, if we see on our code, we start with a count of 0, and then we go through for each item in our list, and we increment the count up by 1, and then we finally return that count. What we can actually do here is see, because I have a linear function of n, whatever size my list is of n is going to be the output of my other list that I have here, right? So now, if I do big list, I'll also get the 100,000, okay? So now what happens here is that we see this quadratic function. And what this says to us is that for whatever input of f of n we have, we get n squared back. So what would this actually look like inside of our code here? If we bring this over, excuse me, I'll go ahead and try to create this for us. So I'll do something like a quad function, and this will be a list. And then I have my count is equal to 0, and I say for item in list, and then I'll just go ahead and copy down the same code from earlier. But what we want to know about quadratic is that it's a squared function. And usually what we see in quadratic are nested loops, which many algorithms are going to have, where a loop has to run an n amount of times. And then there will also be an inner loop inside of that. So what happens here is that for item in list, and then we could also say something like for a in list, like here, and I'll go ahead and I'll put my count plus equals 1. Let's try to do our quad function of our small list. And now we have 10,000, okay? And now if we go ahead and square 100, right? Similar to what we've done earlier. Let's make sure our math is okay. Looks like we're getting whatever size of our n is back out squared. So now if I do my big list right here, I'll accidentally break my program. I think I might already. Let me try to break it. And you can see here already, you see how Python is kind of freezing when I do a quad function. Let me try to do a medium list. See if that works. And even then, because medium list is 10,000 squared, it almost got there. It took a little bit. It's going to take some time to compute, okay? So we can actually see already how in the real time, our functions are getting slower, okay? Now, a cubic function and other polynomials are the other types of items you'll see inside of this code. And again, you can kind of just offhand say that a cubic function occurs when there's like tree products of itself. So a cubic function would be the same as a quad, except there's another list. So it's a nested within a nested list. And usually these functions, if are required, will kind of try to do something where we don't want to do the algorithm this way. So if you're designing algorithms that eventually hit to this point where you have a nest of nests inside of a nest, you're going to have an exponentially long runtime, okay? Now, will this break for 100? Most likely not. If I do cubic function of small list, yeah, it's pretty quick with it. But if I go ahead and I do a medium list, we'll probably be here for a while, right? So this is in real time, the differences between these types of functions and what they actually look like and why some are slower than the others, okay? Now, last thing here is that all these could be viewed as a polynomial size. And excuse me, one more note on the cubic function is that these occur less frequently, but they do in some like edge cases, and cubic functions will not be effective algorithms if the input size is over 1,000. Cool. So what does this actually look like here? Well, we have our constant. We could see here it's immediate. No matter what we put in, we get it out right away. We have logarithmic, which is really good. It's going up slightly throughout it. We have linear, which is what we're used to when we're programming and objects and everything, kind of going up pretty straight. N log n, or linear arithmetic, which is a bit worse than linear. As you can see here, it's a bit above it. But, it's not the end of the world. We can see that we can get some pretty huge sizes. And then if we jump up to quadratic, we see that the sizes are exponentially larger, right? So keep it going. And then cubic is our last guy up here. And cubic is the one that we just looked at. I accidentally forgot the exponential one, but usually that's just where you do something raised to the power of n inside of your code. Not really going to do that in this course, but just know that that's the last guy here, okay? So these are your 7 you need to remember. And going from there, you should be good to go for the running times of them, okay? Cool. So I wanted to look at this asymptotic analysis or asymptotic notation. You're going to see this word quite a bit as you're going forward. And what we do with this is we try to get the bigger pictures to get the growth of an algorithm proportional to an input size of n. Okay, so this is actually called the big O notation or big O analysis, and it's kind of made with the theta sign, the big O sign. Okay. So we can see here, if we have a find max, we return a max element from non-empty Python list. This is something like this is an actual function you'll see in the real world that will have linear runtime. So we could see here that find max is big O of n. That's what this function is because it's linear, right? So we could say here now, so I could say here, something like this, find max of n, and this would be a linear runtime. Cool. Now, here's the mathematical definition I included if you're interested with it. The book goes into heavy amounts of detail with it, but I kind of wanted this to give us a 1,000-foot overview of it. In general, it's let f of n and g of n be functions mapping positive integers to positive real numbers. We say that f of n is big O of g of n if there is a real constant c that is greater than 0 and an integer constant n of O raised greater than or equal to 1, such that the f of n is less than or equal to the constant of g of n for n is greater than or equal to n of 0. Okay, so all this essentially is saying here is that this definition is saying that it is the big O notation, and essentially what we're saying is f of n is big O of g of n. This is all we're saying here. So a function that takes an n is big O of some constant value, which in this case, find max is big O of list of n values, something like that. Cool. So up here we have our 7 values again, right? We have our constant, logarithmic, linear, n log n, quadratic, cubic, exponential values here. And what I wanted to show is if we're asking, like, what's the actual point of having these different timings and values? Why are we using these? And the reason we do it is that we might have multiple algorithms that we're trying to make, and we need to compare them, right? So we could do comparative analysis between 2 algorithms now, right? So big O of n, and then algorithm A has a runtime of big O of n. Algorithm B has a runtime of big O of n squared. And now if we're looking at this, we could actually go over here, and we could say, okay, how many operations will my algorithm do based on this value, right? So if I have algorithm A is an n, if I have an input size of 8, it's going to be 8. That's pretty good. If I have an input size of 512, it's going to be 512. However, for n squared, my algorithm might be really good down here, but then you can see that once it gets to 262,000, it's pretty rough. So you can see here that this is kind of slanted in a way where the more we go to the right, the worse it is. But I wanted to include the quote here is what we actually consider a fast algorithm, right? So any algorithm running in O n log n of time, which is right here, big O of n log n, with a reasonable constant factor, so whatever is going on constantly should be good, is considered efficient. In some scenarios, an n squared time function is going to be fast enough in context, that is when n is small, right? So we could see here that Python is capable of doing 262,000 operations pretty quickly, right? But it's not going to be capable of doing even the 2 million over here effectively. And let's just say that you're designing an application that a lot of people are using. They're going to be annoyed if it's taking some time. If every user is doing 262,000 operations every time they open a page, that's a really big issue. However, if every user is doing 262 once per time they log in, you could probably get away with it, right? So there's some ways that where these algorithms are a bit different. We don't want to go for the idealistic approach to these. We want to be realistic about these two. Cool. So that's overall what I wanted to talk about with module tree. There'll be a small quiz. I just go ahead and read through it. It's just going to be asking you these different items too. I'll go ahead and add 2n to the bottom of the last slide there. And please go ahead and take a look at the code too.